Welcome to Buildings and Beyond,
a podcast that explores how we can create a more sustainable built environment
by focusing on efficiency, accessibility, and health.
I'm Robb Aldrich.
And I'm Kelly Westby.
This week I'm talking with Bill Zoeller, who is a senior vice president here at Stephen Winder Associates. He and I have worked together for almost 20 years now, and it's been observed by several people that Bill and I really don't have many conversations. We have many more arguments, but I think we're both very well behaved in this episode. We're talking about high performance envelopes, specifically high performance walls. I mean, designing building good envelopes has changed a lot over the past couple decades. So we dig into this, the reasons for this a little bit, and specifically talk about some high performance wall systems. Thanks for being here, Bill.
Thanks, Rob. My pleasure.
So I talked to you about doing a session on envelopes, a podcast episode on envelopes, which is a huge topic. But the way envelopes are designed and built now is so drastically different and continues to change a lot with new materials, with new techniques, new details. I wanted to dig into that topic a little bit. And we ended up deciding to talk about walls because that's what came up first. Every building has walls.
Every building has walls.
So big picture, why are envelopes and enclosures? I mean, why are they different now?
Well, in order to look at why they're different now, I think we need to look at the context of where they were. And where they were is really the impetus for why they changed. And where they were a bunch of years ago, let's say 10, 15, 20 years ago, if someone was building your basic house pretty much anywhere in the country, it was framed with 2x4 walls, had R13 bat insulation jammed into the stud cavities without much care or thought of how good or neat or quality the job was. Essentially no care at all to any sort of air sealing between the inside and the outside. So basically you had a frame wall cavity with a little bit of insulation in it and a lot of air blowing through it.
You're not making it sound very good.
Well, it wasn't very good. And when the energy codes changed to improve the performance...
Or actually came into being in lots of places.
They incorporated some attributes that caused some changes to occur. For instance, if we have your basic R13 wall with the bat insulation and no air sealing capability, what you've got is a little bit of thermal insulation that's stopping the flow of heat from inside to outside, a little bit, but all the air is blowing around it. So even if I have insulation in the cavities, the outside air is blowing through the insulation via infiltration and really bypassing the thermal insulation altogether. Then the building codes increased a little bit, and we ended up with 2x6 walls, R19 or R20 insulation in that same space. And we started to employ some air sealing measures. It became known that air infiltration into buildings was one of the largest causes of heat loss and comfort issues and so on in buildings. So the next reasonable response is, well, let's tighten up the buildings. When we did that...
But there wasn't yet a durability concern. I mean, so this was...
Well, yeah, the building science was not really a known quantity when we started to do that. Like anything else, when we start employing new measures and new aspects of anything, there's always unintended consequences, and we certainly found them. In this case, the unintended consequences have to do with the second law of thermodynamics. And usually when I start this conversation, I start with the first law of thermodynamics, which is basically, in a nutshell, that energy can't be created or destroyed. The reason I start with the first law is because I really want to talk about the second law, but if I do that, people always say, well, what the heck's the first law? So we got that out of the way. And the second law of thermodynamics is really the main issue with high-performance wall assemblies and why they're causing problems or can cause problems. And that's that it's the law of entropy, which basically means that any system of energy in an isolated chamber or setting wants to morph towards basically chaos. So if I have heat on one side of the wall and cold on the other side of the wall, what the energy wants to do is basically equalize itself on either sides of the wall. So the heat's going from hot to cold. So if I'm hot on the inside of the house, cold on the outside of the house, the heat wants to flow through that assembly to get to the outside. But in order for that to occur, I need to have energy. And what I'm doing by
So in order for that to occur, well, energy moves from hot to cold.
Mm-hmm.
Yeah, that's in keeping.
Well, the energy wants to move from hot to cold.
All right.
But the transfer of energy actually takes two forms of energy to occur in the case of these buildings, in the case of a wall. There's mechanical energy, and that's the air movement,
Okay.
which aids drying. And then there's thermal energy, which also aids drying. And if I am reducing the airflow and the energy flow through that wall system, I am decreasing the capability of that wall system to dry. That's the new part.
Okay. All right. But it can go both ways. I mean, heat flow and energy flow can cause drying. It can also bring moisture into building cavities. It goes both ways. But I think it's like, 20, 30, whatever, long time ago. I mean, buildings were so leaky that even if moisture got brought into the wall cavity, it dried out pretty quickly because there was just so much airflow and heat flow. Is that?
That's absolutely correct.
Okay.
Right.
All right.
So now we've
We start to get a little bit better.
Right.
Okay.
And so we've diminished the capability of the drying, but we didn't diminish the capability of the wetting. It's still raining on the outside of the building. We still have our cladding dealing with the bulk water as the water flows down the siding of the building. Probably leaks a little bit into the walls because, walls aren't perfect. And we've got the other issue of the air infiltration from the inside of the building carrying the relatively warmer moisture air into the wall cavity, finding something cold and condensating on it. So the air infiltration from the inside can cause condensation within the cavity. So now we've set up a little problem for ourselves. We've increased the thermal insulation and the air tightness a little bit, but we haven't really dealt with the moisture management part. We've taken the wetting and the drying and pushed it a little bit out of balance. And when we push it a little bit out of balance, we end up with dampness inside our walls, and we get mold and decay and all kinds of bad stuff.
All right. So keep water out.
Keep water out. Water is the enemy. Bulk water management is one thing.
Siding, flashing, secondary drainage planes. I mean,
water resistive barriers need to be, adequate.
Okay.
They're never going to be perfect, so we have to understand that they're not going to be perfect, but they have to be well detailed. They have to be proper materials. The water has to be able to go someplace. We see a lot of designs for wall assemblies where they look pretty good if you look at a basic section, but if you look at the details, the water really has no place to go.
Okay.
They're kind of trapped.
Okay.
There's no capillary
All
breaks.
right.
There's that kind of an item.
So let me back up a little bit here. So my perhaps simplistic take is most walls have some kind of siding. The siding should keep most of the water out. If water happens to get behind the siding through some defect in construction or just crazy horizontal rain or upflow rain or, then there should be some kind of, house wrap or building paper or something that the water can't get through, which people I think often call it the drainage plane. I'd like to call it the secondary drainage plane.
Well, that's it. in code speak, that's the weather-resistive barrier.
The weather-resistant barrier.
Right.
Okay.
And if I'm cladding my house in shingles or clapboard or something
All right.
else, all that material overlaps and it's got gaps and joints, and you're going to get wind-driven rain in there.
Yep.
If there's going to
Yep.
be pressure differential, if it's on the lee side of the house or the windward side of the house, depending on what the weather's doing, the water's going to get back there.
Okay.
So it needs a place to go to, whether it's a secondary drainage plane or a weather-resistive barrier. That's all about bulk water management. That's what happens on the outside of the building.
Gotcha. And those come in the form of, like in frame construction, which is, very common. That's at least in residential. House wrap, building paper, or like zip is really, I see more and more zip walls going up, which has the weather-resistant barrier on the face of OSB.
Correct, yeah.
All those created equal? All those more or less the same function?
Well, no, they're all different. And, it depends on the overall assembly of the wall as to which is going to work the best. If you look at the old school stuff, good old 15-pound building felt, that was, in essence, the weather-resistive barrier. In no way was it an air barrier.
Yeah, okay.
So,
with all the laps, with all the joints.
Yeah, and
with
you can't tape it, you can't
Okay.
glue it. Like when the house wraps came out, they were lapped 6 inches according to the manufacturer and stapled.
Yeah.
And it's like, hey, this is an air infiltration barrier, isn't it great? Well, if I take a 1x1 sample and test it in the laboratory, it'll come out as a rated air infiltration barrier. If I put it in a house and I don't bother doing anything with the seams and joints, it's not an air barrier of anything. It's just full of leaks. It's like a
Okay.
bucket with holes in it.
Yep. Okay.
Even though the plastic bucket is made out of waterproof material, it's got holes in it, so it's not going to do you any good in terms of holding water.
And this is, I think, one of the newer things, because 10, 20 years ago, when people came out with tapes that, tape all the seams of your house wrap, of your building paper, of your zip sheathing, nobody trusted that those tapes would hold up over decades. And, they would decompose, the adhesive would break down, and they'd fall off, and then you'd get leaks, air leaks, water leaks, etc. I mean, do you agree? I mean, that seems like very new.
Well, those concerns were well-founded.
Okay.
They didn't work. They didn't. In terms of long-term durability, there was issues.
Okay. But now?
Well, there's different materials on the market. Tapes are a lot better generally.
Okay.
Some are still better than others, but you can get tapes and systems that absolutely work to air seal your building on the outside. And truly, that's the place you should air seal your building, on the exterior sheathing plane. You want to air seal where the air movement is. The air movement's on the outside, not the inside. So that's your first line of defense. That's where it ought to go.
All right. So keep the water out. Flashing details, more important now than they ever were.
Yeah.
Because
the drying capability is lower.
Because there's low drying, and
Right.
getting that weather-resistant barrier, seamless, really impervious, is the way to go. You got to do it in a high-performance wall.
You have to do it in a high-performance
Okay.
wall. A little bit of a problem in that barrier can cause big problems in the overall wall assembly.
So R value, higher R values. How do you do that in the best way? And again, framed wall now.
Well, there's different approaches. Obviously, the standard traditional way is to fill the cavity with fiberglass insulation. That's what we used to do.
Okay.
That works up to a certain point. It still keeps a lot of the thermal bridges in the form of the wood studs, for example, in place. So where the wood studs are, I don't have any insulation at all. I have wood studs.
Or 3 or whatever, yeah.
Less
or
than
5.
yeah, exactly.
Yep.
So really now the more effective approaches utilize continuous exterior insulation, a layer of insulation that basically blankets the entire building around the exterior, covering all the thermal bridges, so that, as an example, I'll have an R5 or an R6 or an R7 continuous around the entire building envelope. That'll be directly integrated with my air sealing. Then, if I put cavity insulation in place, the cavity insulation will actually be effective to its rated value or close to it, because the thermal bridges have essentially been defeated.
Okay. So continuous insulation is the way to go. you think?
It's one of the better approaches.
Okay.
There's different approaches, but that absolutely is a preferred approach, I'll call it.
All right. And the material, foam is what I see mostly. Rigid foam.
Rigid foam works. If you use rigid foam, you could do your air barrier on this and the weather resistive barrier that we talked about before, the secondary drainage plane, as you called it, on the surface of the foam. There's other materials I could use, like mineral wool, rigid mineral wool, for continuous insulation on the exterior, in which case I have to use the sheathing below it, underneath it, for the weather resistive barrier and my air sealing barrier, because the mineral wool is not an air barrier.
Yep.
The cladding or siding needs to be installed on furring strips of some sort, because you can't nail directly through the mineral wool, because it's a compressible material.
Okay.
But it's drainable.
Okay.
So, if you're going to do a rain screen, which basically puts a gap between the sheathing and the back of the cladding as a siding approach, then the mineral wool works just fine.
Rain screen is any gap? I mean, furring strips constitute a rain screen? What?
Well, you can do a rain screen multiple different ways. Basically, it's an air gap or a capillary break between the back of the sheathing and whatever the sheathing is attached to. So if I have a drainable insulation like mineral wool, the back of the cladding, whether it's clapboard or something else, will be spaced out at least typically a quarter of an inch from the face of the insulation, so that if water gets back there, it's got a place to drain. It doesn't cling to the back of the insulation. There's a little air movement up in there. And we talked about the second law of thermodynamics before. If I've got some air movement, I've got some higher drying capability, so I'm introducing some drying capability within that wall cavity.
All right. So the double wall systems, we 10 inches, 12 inches.
We used to see a lot more of those. What you have is basically two parallel stud walls separated by a few inches. So the total dimension of the walls, as you said, is 10, 11, or 12 inches. Then the whole thing is packed with dry blown in dense packed cellulose.
Okay.
That's a lot of insulation. At 3.2 inches or 3.2 or 4 per inch or whatever times 10 inches.
Yep.
30 plus.
Yep.
So what you've got there is a whole lot of thermal insulation, so you're stopping the energy heat flow, and you're getting some air sealing, but it's not a complete vapor permeable solution, so that if there are air leaks, which there will be a little bit, always are, interior more moisture laden air can get into that wall system, find its way to the exterior sheathing, and potentially condense, because the exterior sheathing does not have the continuous insulation we talked about, so it'll be colder. And if it's colder and my interior air gets to it, the relative humidity goes from 50% to 100%, because the air goes from 70 degrees to 10 degrees. I can get some condensation issues, some dew point problems, and end up with a big problem.
All right.
So if you are going to do the double stud wall, there are some products on the market that are highly recommended to make it safe, generically called smart vapor retarders, that you would want to install on the inside of the wall behind your drywall to make that type of a wall system basically a safe wall system. Without that, it's potentially problematic. And
a rain screen or vented siding is even more.
And in combination with the vented siding or rain screen. Yeah.
Okay.
Yeah. We talked about the continuous insulation a little bit before, and what the continuous insulation also does, just to sort of amplify that a little bit, is that it'll take that same exterior sheathing and raise the temperature of it, because you're putting your continuous thermal barrier between the outside weather and the exterior sheathing, so that the temperature of that sheathing remains above the dew point under all design conditions. So even if I have air leakage into the cavity with, say, 2 inches of XPS or polyiso insulation, and say an R19 or R20 in a 2x6 cavity, in most climate zones in the U.S., that'll be a safe wall because the sheathing stays above the dew point, so any air that leaks into that assembly still will not condense.
Okay. It makes sense. I mean, it all makes sense. I see people wanting to stay away from petrochemicals, and most of the rigid insulation, continuous insulation, is foam. But you said there are alternatives. There's some mineral wool, or there's some cellulose-based rigid insulation.
There's some European
Yeah.
type products that are finding their way into the U.S. market slowly that are, essentially wood-based, but they perform more or less like a mineral wool rigid insulation.
Right.
They have the same drawbacks. They're you don't want to nail directly to them. You want to provide a capillary break.
Yep.
You want to give them a chance to drain behind your cladding and so on. But there's plenty of options. And
more and more. It's hard to keep up with it all, but more options.
more options.
More products.
Well, more options is good, but more options includes more confusion,
Yes.
on the part of the designers and builders that are using them. Because if there's a lack of basic understanding of some of the building science involved, they're relying on particular marketing information, which is always going to be a little bit incomplete because it's designed to sell stuff. Let's
Yes.
be honest.
Yeah, definitely. All right. Switching gears a little bit, masonry. What's different in masonry?
Well, let's start with what's the same in masonry.
All right.
And in masonry, if we're talking about new construction, you really want to employ the same strategies you're doing in frame construction, and that's the continuous exterior insulation barrier outside the whole thing. Jacket the whole darn thing in some sort of an insulation jacket, be it XPS or mineral wool or polyiso or something else,
Okay.
to the point where the inside surfaces of the masonry, if it's a CMU, block and plank building, for instance, stays above that dew point. Same rules apply. If I don't have enough continuous insulation on the outside and my CMU backing gets below the dew point, my warm interior air at 50% relative humidity can get in there, contact that masonry, get down to 50 degrees and 100% relative humidity, and I have a moisture problem. So there it's the same. In terms of continuous air barriers and weather resistive barriers, the place to put that typically is on the direct face of the concrete masonry units, the CMU. I'm sorry for using the jargon. I get carried away sometimes.
Yeah.
That kind of a system you'll see with either a brick veneer exterior. We're seeing a lot more rain screen cladding systems, metal panel systems, terracotta panel systems. Will all employ that sort of a strategy. So we're seeing a lot of different approaches that actually work now that the building science is a little bit better understood, and there's more products to provide more variation that are desired by designers.
So the weather-resistant barrier on the outside of the masonry, and most, if not all, the insulation outside of that.
Generally, that's going to be a higher performing approach. Yes.
Okay.
Yeah. Absolutely.
All right.
Yeah. I mean, you could come in with some light gauge steel framing inside your concrete block with some essentially auxiliary insulation material to get a boost in R value or to meet energy code or whatever you're going to do with it. But it's really that outside continuous insulation that's performing most of the work.
And this is typical in the Northeast for multifamily new construction,
In
some
urban
commercial
locations, yeah.
Okay.
Correct, yeah.
And in the rest of the country we've been talking about colder climates generally.
Right.
Is the same hold true? I mean, the R values are lower required by code as you get further south, as you get warmer. I mean, other different challenges, similar challenges?
Well, the challenges are different all over. In general, the masonry buildings are going to be safer in terms of moisture performance because they're a little bit more idiot-proof. If we look at frame construction, when you get down into the south, the rules are a little different. There, if I've got a cooling-dominated climate and the interior temperature is kept at, say, 70 degrees, and it's 95 degrees and 80% relative humidity outside, and I have any moisture drive at all, the thermal dynamics doesn't change. It's just that the flow of energy is now different, and it wants to flow from hot to cold. So in that case, it's outside to inside. So now, if I have air leaks, I'm drawing the exterior, the hot, sticky air through that wall assembly to the inside. And if I have a vapor retarder on the inside, even if it's by accident, like vinyl wallpaper, I have a big problem because that's where the moisture stops. I'll get condensation, I'll get mold, I'll have all sorts of problems. So it really is climate specific how you deal with it. When you're looking at climates in between, that can be both. Say Washington, D.C., it can get New York cold, or it can get Florida hot.
Yep.
So, you really have to understand the dynamics in designing high-performance wall systems, especially in those mixed climates.
In Phoenix, the risks are lower, I imagine.
In Phoenix or, most of California, the risks are lower because, the enemy is water.
Yeah.
And there's just less of it
Right.
in the air.
Right.
So it tends to not be as much of a problem.
So if your brother called you up, said he was building a new house, asked you what kind of wall he should use in a single-family home in Connecticut, in New York, what would you tell him?
I just had this conversation with my brother yesterday.
No, you didn't.
No, I didn't. But I mean, in a typical northeastern climate zone 5 scenario, likely be a 2x6 wall. It could be maybe a 2x4 wall. People, builders don't want to do that anymore, but there's nothing wrong with it because structurally it's fine. And if I can get my continuous insulation on the outside, do my air barriers out there, do a continuous R15 on the outside, which is 2.5 inches of XPS of polyiso, 3 inches of XPS, and do an R13 bat or an R15 bat. That's an R30 wall and a 2x4 wall.
Okay.
Nothing wrong with that.
All right.
So if you're looking at low cost, high performance, that is probably a really good approach. A lot of builders will just say, I'm not going to do 2x4s because blah, blah, blah. So they want to do 2x6. And okay, well then do, R10 continuous outside and then do R19 bats.
Okay.
You want to make sure that the continuous insulation stays within a fairly high ratio of the total insulation. Like 33% probably is a minimum for condensation control. So that's basically a rule of thumb. You'd want to look at the actual attributes and parameters of your materials before making that decision. But that's a pretty good rule of thumb to start with for basic planning purposes.
Okay. And further south, is there a line where continuous insulation is really kind of moot, not really required? In Georgia, do you really need continuous insulation? Is it a code doesn't require it?
No, the code doesn't require it.
Okay.
And again, if you don't do the continuous insulation, you're still going to have the thermal breaks.
Yeah. Right.
The thermal bridges, rather. But the thermal bridges will be less important because the temperature differential is less. If I'm 70 degrees on the inside and 90 degrees on the outside, that's a delta T of 20 degrees. Not a big deal. In New York, if I'm 70 degrees on the inside and 10 degrees on the outside, that's a 60-degree temperature differential.
That's quick math.
Yeah.
That's good.
I hang out with a lot of engineers. It's like through osmosis. So, the thermal drive is 3 times greater.
Okay.
But you're still not getting the complete performance package if you do continuous insulation. Again, you got to pay attention a little bit differently to the dynamics, but you could still do a high-performance wall. You could do a high-performance wall without the continuous easier in the south than you can in the north.
Yep. Okay. All right. So, keep the weather out. Number 1. Excellent.
Bulk water management,
siding, flashing,
critical.
drainage. Probably number 1.
Yes.
Air tightness. Number 2.
Agreed.
And then from there, it's designing for forgivability, or if something does go wrong, you get a little bit of air leakage or you get a little bit of water leakage.
Yeah, it's understanding.
It's not a
it's
catastrophe.
understanding what the vapor control issues are.
Okay.
Dew point control, condensation control, vapor dynamics. And it all changes a little bit based on how much R value you put in because of that very unforgiving second law of thermodynamics.
All right, so if we talk about this again in 5 years, what are we going to be talking about? Any new systems, you think? New systems, new products?
Well, the physics will not change.
All
I
right.
can pretty much guarantee that.
All right. We're recording, so we can...
You can play it back. It's fine. There's always going to be new systems on the market introduced, about half of which will make it, half of which won't, and 10 or 20%, that'll be pretty good. The other 30% that make it that aren't pretty good will make it on behalf of their marketing strength, but that's okay too.
All right.
I don't see anything really new and upcoming that's going to be earth-shattering. There's a lot of stuff that people always think is going to be. We saw, panelized construction, SIP construction, all that kind of type of product. They're fine. You just have to understand how they work and where they work and, what to avoid in terms of problems.
But they haven't taken over the world, yeah.
Yeah, no, they're, the 2% market share, whatever it is,
Yeah.
and they've been around for a while, so they haven't, there's a reason they haven't taken over the world. But they're perfectly fine product and perfectly acceptable for use in modern buildings. Whether something new comes along that, usurps all of that, that's crystal ball time.
Yeah, right.
I don't see it right now.
All right. Awesome. Thanks very much.
Hey, thanks for having me. Appreciate it.
Thank you for listening to Buildings and Beyond. For more information about the topics discussed today, visit www.swinter.com/podcast and check out the episode's show notes. Buildings and Beyond is brought to you by Stephen Winter Associates. We provide energy, green building, and accessibility consulting services to improve the built environment. Our professionals have led the way since 1972 in the development of best practices to achieve high-performance buildings. Our production team for today's episode includes Dylan Martello, Alex Mirable, and myself, Heather Breslin. Thank you for listening, and we'll see you next week.